we have Michael Rosenberg and Shannon Veitch, who is going to talk to us about the alligator-like PQ obfuscation, which is, let's leave it up to them. Go ahead.
Yeah, so today we're going to talk about tools that are used for protocols which aim to hide metadata. And this might be for protecting user privacy, dissuading protocol fingerprinting, or preventing network ossification. So for example, the TLS 1.3 ECH extension aims to hide target domains. Quick has deliberate anti-ossification properties by preventing or minimizing the wire image. And OBS4 and ShadowSox are censorship circumvention protocols which aim to prevent protocol fingerprinting by encrypting or obfuscating all the traffic on the wire. And in particular, when we're talking about key exchanges, we might call this an obfuscated key exchange. So these tools are also useful for some password authenticated key exchange protocols, which might need to operate over random byte strings. Previously, in particular for key exchanges, Elligator was used for mapping elliptic curve public keys to random byte strings. But for post-quantum protocols, the situation is a bit less clear. So if you're using Saber or FrodoChem, you're basically already good to go because these public keys in ciphertext already look like random byte strings. But the situation is not exactly the same for MLChem. So in this talk, I'll start with introducing our Kemeleon encoding, which takes MLChem public keys and ciphertext and maps these to random byte strings. Okay, so what do MLChem public keys actually look like? They're polynomials with coefficients modulo some value of q with a random seed appended at the end. So if we look at the frequency of this byte distribution, the y-axis shows the byte values and the x-axis the position in the encapsulation key. And then the color here represents the frequency at which each of these values occurs. So if we zoom in, we can see that the seed appended at the end of this public key is perfectly uniformly distributed, but the same is not true for the coefficients in the public key. So what's happening here is because q is not a power of 2, every most significant bit of the coefficients in the public key are slightly biased towards 0, meaning that these higher byte values don't occur. So how does the Kemeleon encoding handle this? Well, we basically accumulate this into one big integer. Now, only the most significant bit is biased towards 0, but we can just do rejection sampling on this bit if it's equal to 1. So now our encoded public keys actually end up being about 2.5% smaller than regular MLChem public keys because of this accumulation. And the rejection rate here for MLChem 768 is about 17%, which is reasonable if you consider the fact that for Elligator, the rejection rate was approximately 50%. So what about ciphertext? You might think it's basically the same thing, but no, life is not that easy. These vectors of polynomials are actually compressed before being returned by encapsulation. And what this compression does is some rounding, where the output space does not evenly divide the input space. So if we look at the distribution of the coefficient values in the ciphertext, certain values of coefficients at a set period will appear more often than others. So to handle this, the Kemeleon encoding first undoes this compression. So we just decompress and then sort of artificially recover the randomness that was lost in this compression. And then we can use the same rejection sampling technique that we had for public keys. And because we have to decompress, we end up with ciphertexts that are 6 to 15% larger than standard MLChem ciphertexts. So that gives us our Kemeleon encoding algorithms with rejection sampling, but we also have a variant without rejection by borrowing a technique from the Elligator squared algorithm. So here we take our accumulated large integer from before, and we basically pad this by adding a random value so that the output space is some power of 2. And then decoding is pretty simple. We just take the resulting value modulo the size of the original accumulated integer, and then we decode as usual. And because we have to add a little bit extra padding here, we end up with public keys that are about the same size as standard MLChem public keys. But now we no longer have this rejection rate. Okay, so we can take our Kemeleon encoding and naturally combine this with MLChem by encoding public keys in ciphertext, to obtain what we call an obfuscated chem, or an OChem. And the security properties that we care about for OChems are standard in CCA security, SPR CCA, which means strong pseudo-randomness, and this captures indistinguishability of shared secrets and that ciphertexts are random or simulatable. And this implies standard notions of anonymity for chems. And then lastly, ciphertext and public key uniformity, which capture the indistinguishability of these objects from random bit strings. So our MLChem instantiation of this OChem satisfies all of these security properties, where each of these reduce to either a property of the underlying chem or a modular LWE assumption, with some small loss from the rejection rates in each case. So here, notably, these ciphertext and public key uniformity properties rely on a computational assumption modular LWE, whereas with Elligator, these were statistically uniform. Okay, so a couple important things to note if you're using Kemeleon in practice. You might want to consider a constant time implementation for in particular for the big integer arithmetic, or if you're using the rejection sampling case. And it's important to be careful with how you're using the randomness used in these encodings. If the randomness is revealed, then it's trivial to distinguish the output from random bit strings. And in terms of performance, if we just look at the times for key generation, ML Kemeleon key generation is approximately 3 times slower than standard MLChem and 2 times slower than X25519 plus Elligator and Sabre. But these are just rough preliminary estimates for now. So with that, I'll let Michael talk a bit about the hybrid case.
Thanks. So we've seen how to make an obfuscated key encapsulation mechanism that's post-quantum, but sometimes we want to hedge against attacks against new implementations because it's new code, and attacks against the mathematical underpinnings of these new schemes. So we want a hybrid obfuscated key encapsulation mechanism. That is a hybrid OChem that combines the classical hardness of an OChem with the post-quantum hardness of a separate OChem. So how do we do that? So let's look at how existing hybrid chems work. Essentially, every hybrid chem that exists right now is a chem combiner that looks like this. If you disagree, please feel free to CC me on the IETF mailing list. The public key is the concatenation of the 2 underlying public keys. And encapsulation is simply parallel encapsulation to the 2 public keys. And the ciphertext is the concatenation of the 2 underlying ciphertexts. And the final shared secret is the hash of the 2 shared secrets plus some other stuff. It is known that basically everything on the swarm gives you IND CCA security, but we want something more because we're making OChems, not just chems. So we want hybrid obfuscation. You can see that this doesn't have hybrid ciphertext uniformity, for example, because the ciphertexts are simply a concatenation of the 2 underlying ciphertexts. So if you can spot a non-uniformity in one of them, you've spotted a non-uniformity in the entire ciphertext. But maybe we can get some intuition here. It is not a priori necessary to reveal both of these ciphertexts at the same time, right? You might think maybe you can reveal just one of these ciphertexts and use some intermediate keying material to encrypt the other ciphertext, so you only have to reveal one and not the other. In addition, we'll note that sometimes ciphertexts are statistically uniform. That is, they don't rely on any computational assumption for uniformity. This is the case for Diffie-Hellman key exchange with Elligator encoding. So can we use this intuition to build a new chem? We have a combiner called outer encrypts inner nested combiner, or OINC. The public keys are the concatenation of the underlying public keys as before, and the encapsulation goes similarly as before. We have something that we call an outer OChem and an inner OChem. The outer one has unconditionally uniform ciphertext, and the inner one has just some notion of uniformity. It could be computational. So what happens is you do these encapsulations in parallel as before, and then you encrypt the inner ciphertext using the intermediate key from the outer outer OChem. This encryption is just a one-time pad. Then you concatenate the first ciphertext plain with the encrypted inner ciphertext, and the key is just the hash of everything as before. This gives you IND-CCA because the keys derive basically the same way as before. It's also quite cheap. It only requires a single KDF and an XOR operation. And it also achieves hybrid ciphertext uniformity, and I'll give some intuition for that right now. So suppose the inner OChem is broken. We can imagine the ciphertext and key are just 0, right? In that case, this XOR is still using good randomness from the non-broken outer OChem, and so the inner ciphertext, once it's encrypted, will still appear random. And now consider if the outer OChem is broken. Well, we only said that it's unconditionally uniform. So even when it is broken as broken can be, the ciphertext is still uniform. However, the shared secret might be 0. So in that case, the inner OChem, we assume, is not broken, and so this will still retain uniformity. And even if the key is 0, we have an XOR of a random value with possibly a predicted value, so we still have randomness. So this happens to achieve hybrid SPR-CCA security as well, which we show in our paper. And notably, this does not achieve hybrid public key uniformity because, again, the public keys are just the concatenation of the two underlying public keys. If you can spot a non-uniformity in one of them, you've spotted a non-uniformity in the entire public key. And we believe that this is inherent. It's not clear if you can even make a scheme that has hybrid public key uniformity. So concretely, you can instantiate the outer OChem with just DHChem like HPKE DHChem over the ristretto prime-order group and Elligator-2 encoding. And this has a property which we define more rigorously in the paper of strong ciphertext uniformity. And the inner OChem can be instantiated with ML Kemeleon, as we said before, or Saber or FrodoChem.
Okay, so we can build a few applications from this chem combiner. In particular, first we looked at hybrid obfuscated key exchange. So the idea here is that we want all handshake traffic to appear indistinguishable from random. And typically we assume that honest clients know the server's public key and the adversary does not. And so this threat model has applications in censorship circumvention. So in particular, it maps to the threat model of OBS4, which is used as a Tor pluggable transport. And here the idea is that the transcript should appear indistinguishable from random so that it doesn't match any censor block lists. So our previous chem-based protocol required hybrid public key uniformity if it were to be instantiated with a hybrid OChem. And we know that this is difficult to achieve. So what do? Well, we constructed a new protocol, which we call Drivel. The idea here is that the base of the protocol is an ephemeral chem encapsulation. So here, this is just a regular plain chem plus a static OChem encapsulation. So here, C1 in particular has ciphertext uniformity. And then the resulting shared secret is computed from these two input keys. So here, because the ephemeral chem is just a regular chem, we know that PKE and C2 don't have these nice uniformity properties. But what we can do is just derive a key from our intermediate chem key K1 and use this to encrypt the values PKE and C2. And then we no longer need public key uniformity. And actually, we get some nice efficiency improvements because for the ephemeral chem, we only need an int1 CCA secure chem. So this gives us our hybrid obfuscated key exchange protocol.
So this is my favorite part. How do you make a password authenticated key exchange protocol out of this? So let's recall what a PAKE is. It is a protocol wherein two parties have a shared low entropy secret called a password, and they want to use this mutual knowledge to derive a high entropy shared secret. It has two properties. Active attackers are able to guess the password if they are active during the session, and they have one guess at the password. And passive attackers essentially have no advantage at all. So there are plenty of chem-based password authenticated key exchange protocols that have been published recently. We'll focus on Cake, which has been proven in the UC model with adaptive corruptions. It's the only one with adaptive corruptions as far as we know. And if you're familiar with EEK, which is the original PAKE, kind of has this structure. You can think of this as just an ephemeral chem key exchange, except you're encrypting the public key with the password, and you're also encrypting the ciphertext with the password. So in order to be secure, Cake requires the chem that it uses to have ciphertext and public key uniformity, which means that it is an ideal candidate for an OChem. You can just plug in an OChem and it works. However, like we said, we need hybrid public key uniformity, and we can't get it naturally using our combiner. It basically requires both underlying public keys to be uniform. And so the only way you can get this is by just having statistical uniformity for both of the underlying public keys. So DHChem naturally has statistical public key uniformity. It's just a random group element. But none of the lattice-based ones have this property. They're all based on the LWE or MLWE or LWR assumption. However, this isn't inherent. A lot of these LWE schemes rely on an optimization due to Lindner and Pikert, where instead of having a public key that is uniform and a ciphertext that is an LWE sample, it makes both the public key and the ciphertext LWE samples. So our idea is simply just undo this optimization. So if you do this to Photochem, you get something that we call stat Photochem, and you can use this to instantiate the PAKE. So the final construction is Cake over the OChem that is the combiner of DHChem with Elligator and stat Photochem. So some properties of this. This is the first hybrid PAKE that has been shown to be secure in the UC model with adaptive corruptions. It is only 2 rounds, whereas the other ones are either 3 rounds or they are 1 round and very inefficient because they use isogeny-based group actions. And this comes at the cost of about a 7.5 times overhead compared to the 3-round PAKE using normal Photochem. It also has a similar increase in computational complexity. It would be interesting to see if we could get something like this working with module-based, with ideal lattice-based schemes, but the leftover hash lemma doesn't quite apply in the same way there, so we leave this to future work. In conclusion, we defined a uniform encoding for MLChem. We used it to construct an obfuscated key encapsulation mechanism based on MLChem, and we designed a combiner that can take 2 OChems and produce a hybrid OChem. We used it to construct a hybrid obfuscated key exchange mechanism and the first hybrid PAKE that is secure with adaptive corruptions. And with that, we'll take questions.
First of all, thank you. This is directly useful for post-quantum Zcash because we need the hybrid encryption that is key private. So for the indistinguishability of the combined public key, it's clear that you can't get that just assuming that either of the schemes are indistinguishable. Can you get it when you pick one scheme in advance, and if that's indistinguishable, then you get the overall property? I guess, yes, if the public key for the pre-quantum scheme, say, is indistinguishable.
Sorry, can you repeat the?
So what I'm saying is, it's clear that you can't get indistinguishability of the combined public key just by assuming some property of either scheme, right?
Mm-hmm.
But if you pick one scheme and assume some property of that, then is that sufficient?
Right, then that reduces to the, say one of them is perfectly indistinguishable from uniform, then this reduces to just the indistinguishability of the other one. But that's not what hybrid means, because hybrid means you have to break both.
I understand, yeah.
Yeah.
In practice, yeah, you might trust more than one more than the other. Okay, thanks.